partial explanation of why we get this block structure. If you look in general at what happens when you take the run length transform of a sequence, suppose our starting sequence, the driving sequence, was 1, A, B, C, D, E. Look at the run length transform. In the terms 4, 5, 6, and 7, we say, all right, 4 has a single 1 in it, so we get B of 1, which is A. 5 is 1, 0, 1, so we get A squared. 6 is 1, 1, 0, so we get B of 2. And 7 is 1, 1, 1, so we get B of 3. And then the terms from 8 to 15 start again with A squared, and so on. And so we get this recursive structure of blocks of increasing powers of 2. And this explains some of the block structure of these cellular automata. For Fredkin's replicator, the underlying sequence, the driving sequence, is 1, 8, 24, 1, 1, 2, 4, 1, 6, 17, 28. And you can guess, if you stare at it, that this satisfies the rule that each term is the sum of twice the previous term plus 8 times the term before that.
That's the taxicab number in the relation?
Almost, yes. Yes. That does not help. But you guessed this, and then the hard part is to prove it. This is what held me up for a long time. All right, before I show you the proof of that identity, let me give a simpler example. Suppose we did a one-dimensional cellular automata, starting with 3 cells in a row. Sorry. What did I do? All right, but we've come to the end of the talk. I guess I hit it down there, right? All right. A simpler example. If we did the odd rule with this neighborhood, 3 cells in a row, so the neighborhood is 1 over x plus 1 plus x. So f is 1 over x plus 1 plus x. We want to know how many cells are on. This is one of the 3-dimensional Wolfram rules. It's rule 150 out of the 256 one-dimensional 3-celled rules. And it's an old sequence in the database. It was analyzed by Torsten Silke and Benoit Cloitre around 2001. And in effect, what they showed was that this is the run length transform. This sequence that you get from this neighborhood is the run length transform of another classical sequence, the Jakob-Stahl numbers, sequence 1045, which is you take the previous term plus twice the term before that. Just a bit more complicated than the Fibonacci recurrence. So, and the sequence, so the underlying sequence, the driving sequence for this is 1, 3, 5, 11, 21, 43. And you can see that 43, for example, is 21 plus twice 11, 43. 21 is 11 plus twice 5. So you stare at this and it jumps out at you that it's previous term plus twice the term before that. Or you look it up and A1045. Try this again. Okay, so now let me talk about Fredkin's replicator. So I've told you what the neighborhood is. Here are the numbers. This is the tableau of the number of cells that are on at the nth generation. 0, 1, 2, 3, 4, 5, 6, 7, and so on. The theorem 2 says it's the run length transform of the numbers at 1 less than powers of 2. So we know that's true, but we don't yet know what these numbers are. We have a guess, but that's all. And okay, so Kellen kindly showed me how to make an animated GIF from Mathematica. So here is Fredkin's replicator at work. We're coming up to 64 generations. That's this 63rd generation. And here are the static pictures of the first few generations. Now, we know now what we have to do. We have to figure out what's going on at generations that are 1 less than powers of 2. So, in order to isolate them, I use h sub n to be generation 2 to the n minus 1. So h2 is the 3rd generation, h3 is the 7th generation, h4 is the 15th generation, and so on. What we have to do is prove that the conjectured recurrence for the number of on cells in this sequence of pictures is what we said it should be. Well, all right. There's h of 3, and you can see how many cells are on whatever it is. h1 is easy. It's got 8 cells. This has whatever it has. And, h. Okay, here's h of 4 with 416 on cells. Why does that have 416 on black cells? That's the mystery. Here's h of 5. It has 1728 on cells. What we would like to do is find some kind of recurrence that relates this picture to earlier pictures in the same sequence. Remember, we're trying to prove that the number of black cells here is twice the number of black cells in the previous picture, h of 4, plus 8 times the number in the picture before that. Well, you can stare at this for quite a while, and I did, and you can stare at this for quite a while. This is the next generation. This is the 63rd generation, and it's got 6784 on cells, which is twice the number. Theoretically, what we're trying to prove is that this is twice the number of cells in the previous picture, plus 8 times the number of black cells in the picture before that. Why is that? So what we want to do is cut it up into copies. So we sit there with our delicate scalpel ready, and we want to cut it up. Now, in the middle, you can see actually a copy of something that's 2 generations, which is 1 generation earlier. And if you stare at it, you can see here there's a copy of one that's 2 generations earlier. That was obvious. But the tricky part is up in this corner. And I spent a lot of time trying to cut this up. And it was very tricky. But I'll show you the proof. So, all right, so so what I'm going to prove is that the driving sequence satisfies b of n plus 1 is twice b of n plus 8, b of n minus 1, with initial terms 1 and 8. We'll take the run length transform of that, and we'll get the sequence we're interested in. So I defined h of n to be f to the 2 to the n minus 1. And b of n, the driving sequence, is the number of non-zero terms in that. Now, that satisfies a recurrence, because h sub n plus 1 is f to the 2 to the n plus 1 minus 1, which is f to the 2 to the n times h of n. But by the freshman's dream, that means we can get this by taking 8 copies of this and spreading and adding and superimposing them and adding them up. So let me give names to the pieces in h of n. I want to say h of n, for n bigger than 0, you can easily show it has a 0 at the center, and along the axes, it just alternates 1, 0, 1, 0, 1, 0 along the axes. Let me call what's in the first quadrant 1 sub n, second quadrant 2 sub n, 3 sub n, and 4 sub n. Now, because we have this, we know that the next term is obtained by adding 8 copies, superimposing mod 2, 8 copies of h of n. They're shown in different colors here. And then we can break them up. We know what this copy here is h of n, which is 1, 2, 3, 4 with zeros. Here's another. So we have 8 copies, we add them up and we get that. And then this, of course, in the top right corner here, is I sub n plus 1. So we get a recurrence for I sub n plus 1 in terms of 1, 2, 3, 4 sub n. You stare at this and you say, if we add up 1 plus 2 plus 3 plus 4, what do we get? Well, in this corner we get 1 plus 2, the 1's cancel, so we have 2. We add this and this, the 2's die, and we get 1 plus 4, and here's 1 plus 4, so we get 0. So we say, aha, 1 plus 2 plus 3 plus 4, the sum of the 4 quadrants is 0. So that means if we go back here and look at this, this is 1 plus 3 plus 4. Well, by this identity, that is the second quadrant of I sub n. So that's really 2 sub n. This is 1 sub n. This is 4 sub n. This is 3 sub n. So in the middle, we do indeed have h sub n. So this has proved that the middle, at least, is correct. Yeah, one more thing before I leave this picture. If we look in the corners, we have 1, 2, 3, and 4. So we get another copy of h sub n from the 4 corners. So that explains everything in this picture except this block here. So I take this block, and which is 1 plus 2, this 1 naught 1 naught strip, and then 1 plus 2. If we examine that more carefully, it looks like this. Then we can say, aha, this is a copy of h sub n minus 1, and if we move this to here, we get another copy. And this is true on each of the 4 edges. We get 2 copies of h of n minus 1, so we end up with 8 copies of n minus 1, and we already have 2 copies of h of n. So we have proved the identity we were trying to prove. If you look at the dissection, you can see why it was tricky to find. What you actually have to do is make cuts through the blocks of black cells. You have to cut here and here, and everything works. So that proves the theorem. I want to show you another example, which also has nice pictures. This is the case in 2 dimensions where we look at the neighborhood, which is the von Neumann neighborhood, plus its center cell. This is another classic sequence, A72272. This is Wolfram's Rule 614. The numbers of cells that are on give you this tableau. By the theorem, this is the run-length transform of 1,5,17,61,217, which appears to be sequence 7483. But there are no guarantees that's correct until we actually find the proof. Well, so here are the first 8 generations. And again, we have to focus attention on generations which are 1 less than powers of 2. And they look like this. So here's h of 4, here's h of 5, and so on. This one is actually a bit easier to handle because there are perforations, like in a block of stamps, suggesting that, first of all, you've got a copy of an earlier thing in the middle, and then if you tear it along these perforations, you get 4 copies of what I call haystacks, because they have kind of a haystack shape. Paul Stockmeyer had mentioned that he also had come across these particular haystacks. I mean, he called them stealth bombers, because they do have kind of a stealth bomber-like shape. But I prefer haystack. So the theorem is that, indeed, this we can prove the recurrence, and I will skip most of the details. Here's the decomposition, the dissection into a central copy of 2 generations earlier, and the 4 haystacks that I call north, west, south, and east. They're symmetric under the action of the rotation group, and I have to prove that we can decompose the H of 5 into disjoint copies. You have to be careful to ensure that they're disjoint, so there's no cancellation. So when you add up the number of non-zero terms, it's equal to the separate sum of the non-zero terms on the right-hand side. That gave a decomposition of the whole picture into a central copy of an earlier picture plus the 4 haystacks. You can also decompose the haystack into 3 bigger haystacks plus 2 tiny haystacks. And that gives an identity for the number of cells, a recurrence for the number of cells in the haystack, which is that, and the way you prove it is by defining the haystacks like that, and the decomposition, I have to prove that the pieces are disjoint, that they are. I can bound the boundary of the haystack, and the result is that we get what we wanted. One nice thing about, I have to bound the haystack. I have to show that there are no cells outside a certain pentagon of the haystack. And the way that works is you look at the next generation after the haystack. The haystack is a certain configuration of cells. Look at what it goes to under the rule, which is to say multiply it by the neighborhood, f. And again, the freshman stream tells you that the generation after a haystack just has 6 non-zero cells. So the haystack itself is in the interior of that. So that proves that the second dissection is correct, and you put the 2 pieces together and you get the recurrence. So that worked. I also promised to mention the one-dimensional cellular automata. Well, I also have looked at a lot of other 2-dimensional ones. But Stephen Wolfram famously gave numbers to all of the one-dimensional cellular automata that are defined on a 3-cell neighborhood. And Rule 18, which is that, gives the succession of states look like that, and the numbers are like that, and you get the sequence 1, 3, 1, 6.
This Pascal's triangle mode 2.
Yes. It's the run length transform of powers of 2, actually. It's 2 to the weight of n. Correct. Yeah. So out of all these 256 one-dimensional cellular automata, there are actually only 7 different sequences that are non-trivial that come out. This is a very nice, simple one. A lot of them are really trivial, like just constants or linear growth. This one is interesting. The 2 most interesting ones are what you get from rules 30 and 110. These are, we know that rule 110 can act as a Turing machine. You can obtain any Turing machine you want by taking the right initial state. But I'm just looking at an initial state of 1 cell. Here is what happens as it grows. Here is the picture from Wolfram's book, A New Kind of Science, showing a bigger picture of this. And you can see, well, it looks pretty random. But I'm not interested so much in the detailed structure. I just want to know how many cells are on at the nth generation. And if you look at a graph, Well, it grows pretty linearly. So I would like to know, how hard is this sequence to identify? It may be that there's no simpler definition than this definition. It's just, that's the sequence, and that's all there is to it. There are many other sequences. Here's an example of a two-dimensional sequence. This is rule 780. The initial states, they start off looking pretty nice, and you can find a formula up to about here, but then they get prettier and prettier, and I have no idea how to handle this. And let me end by saying that we need more editors for the AIS.
Thank you.
The current stack is up to 300 waiting to be edited. We need volunteers now.
Thank you.